All right, I'm looking first at your symmetry page. Do you have any questions about that one? No? Everybody good? Speak now for everyone. Number 9. Y'all on the symmetry one? The absolute value? The word problems on the AROC page. All right, I was going to say, look at the symmetry one first, the one with the 6 graphs on the front. Which one from there? 1 through 6 and 13? 1 through 6? What's the symmetry type? Origin, because if you twisted it 180 degrees. How about number 2? Origin. Number two looks like this. That's origin. But if you put like a pin right here and you twisted it 180 degrees upside down, it would look exactly the same. How about number 3? Y-axis. How about number 4? None, because it slid down, right? How about number 5? X-axis. How about number 6? All of the above. That's exactly right. It's a circle. 3 is y-axis. I don't know. I'll look. Number 6. Yeah. All right, how about the backs? 13. I don't have paper. 7 should be even. 8 should be odd. 9 should be neither. Yep. 7 is even, 8 is odd. Number 9 should be neither. You got the square root of x minus 4. So if I do a negative, I get negative x minus 4. Everything's not changed here. Everything's not opposite, right? And if you think about it graphically, it makes sense. You remember what a square root graph looks like? It looks like that, right? And this has just been shifted to the right 4. So really, that's where it is. That has no symmetry. So none. Yes. We're talking about that today, actually. After. L. McGee strikes again. Number 10. Even. Number 11. Wait. What? Number 10. So if you put a negative in there, then you end up with, this is negative, so this would be negative 5x. And what does absolute value do? Makes it positive. As long as there's nothing inside these parentheses. If it's just, and here's why. This is absolute value, yes? It doesn't matter what number's hooked to it in here. That's just going to stretch it out or shrink it in, right? It's still going to be even. This is going to shift it up or down. So it's still going to be even no matter what. All right, number 11, odd. Number 12, neither. 13 was a problem. 13 is neither. Same thing, right. Well, same thing here too. if you look on number 13, that's got a horizontal strength on it, but it's also shifted to the right. So what happens if you take that absolute value and you shift it to the right? It's not symmetric anymore. What's 13? It depends on what, as long as, if there is any translation in the absolute value, then it's not anymore. How about 14? Odd. Neither. Bruh, I just went through this whole explanation. All right. If you have this plus some number or minus some number, it doesn't matter what it is, that's shifting it left or right, right? If I shift left or right, I'm not symmetric anymore about the y-axis. Right. That's correct. That's an up or down. All right, next sheet. 15 and 16, the word problems. Yes. The average low temperature by month in Nashville is represented by the function blah, where X is the month. X is the month. So we're talking about January, guys. January is 1, February is 2, March is 3, and so on. It says find the average rate of change from March to August. No, because it won't change at the same rate between those intervals. So if you think about a parabola, if I go from here to here, the slope of those, yeah. Yeah, maybe Ellen's are wrong. All right, let's see. I'm going to find f of 3 first. Yes? No, maybe so. So I'm going to plug it in, negative 1.4. 3 squared. Do you see where the 3 is coming from? March. All right, y'all do not complain if that's on your test and you don't know what it means. How do you find that? I was checking with Ellen. Who put it on the board? Me. Where? No, it's not. Sullivan? I'm probably going to be on TikTok next. Yeah, that one's been there. Sullivan, why is it 3? I don't know. You tell me. March is the 3rd month. No, it's today. That's good. Good job. Yes. All right. So now that you know, can you do A-Rock on this one? All right. So f of 3, what's f of 3? Somebody tell me. 46? Point what? 0.1. Then I'm going to do f of 8. What do you get? And now I just do slope between those 2 points. Remember, half of your credit is coming from your units, so make sure you get that right. So I got 64.1 minus 46.1 over 8 minus 3. And you get, I don't have the answers. 18 what? Degrees per month. You're always going to have a per because A-Rock is a rate. It's a rate of change. Yeah. You could even do 3.6 degrees per What? Yes, no, maybe so. 16 is my favorite. Hint, hint, hint. Yeah, I like it. It's the most applicable. Huh? I'm looking at the. So look at, it's always a ratio of the units that the x variable is written in divided by the units that the y variable is written in. So x is in what, feet? And y is in seconds? Oh no, I got that backwards. It's delta y over delta x, right? So it's the units of y divided by the units of x. So, yes. So in this case, y represents the height, so it would be feet per, and then x is time, so per second. It's always the y divided by the x, just like the slope is y divided by x. All right, so for 16, I've got this equation. You will see this one again, at least once, maybe twice. A quiz and a test. A rocket's launched into the air from a podium 6 feet off the ground, and they give you this equation. Charlie Ray, what did I say about this problem? How many times? Quiz and test, right? Okay, that's correct. That's correct. All right, so agree or disagree? That's what that looks like. Why? Okay, it's an upside down parabola, yes? And so it asked me that it says h represents the height in feet, t is the time in seconds. Find the average rate of change from the initial launch to the maximum height. That's your key there. Maximum height happens at the vertex, yes? How do I find the vertex of a quadratic? Negative b over 2a. X is opposite b over 2a. So for this one, it's going to be negative 120 over 2 times negative 16. How do you find the vertex of a quadratic? Opposite b over 2a. That's where the maximum is going to occur. Maximums and mins always occur at vertices. Because it said find the average rate of change from the initial launch to the maximum height. So 120 divided by 32, what do you get? Right? I need the y part so that I can find the average rate of change. Plug it in, that's exactly right. What do you get? Slope, then, or a rock. Y'all need this or no? Oh, you're right. It's not 0006. So why? Oh no, look. No. What do you get when you do this? Did you write it down? 16. 60 feet per second. Isn't that beautiful? I'm trying. What I'm round? No rounding. We didn't round. Oh, well, that's fine. That's, yeah. It says find the average rate of change from the initial launch. So initial launch happened whenever the time was 0. And if you plug 0 into this equation, you get 6. So from initial launch to max height. Max height happens at the vertex. All right. What else? 14. Gotta say it like that. All right, here we go. Find the average rate of change on this interval. So I'm going to do f of -9 first. So -9 cubed plus 5 times -9 squared minus 2. And I'm going to do f of -5. Same thing, -5 cubed plus 5 times -5 squared minus 2. I don't know what you get here. Somebody tell me what you get. Negative what? -326. Charlie, what do you get when you plug in -5? If he really tried, he'd do really well. Huh? 252? Is that sure? What did you? And then, okay. So, Charlie, what's the average rate change on that interval? What is the average rate of change on that interval? Right. Tell me how to find it. AT1. And we don't have a unit, so we don't know. $12, 9, and 10. All right, number 9. X cubed plus 2x squared minus 5x plus 3 on the interval 1, 5. I'll do f of 1 first, and then f of 5. 1 cubed plus 2 times 1 squared minus 5 times 1 plus 3. 3. This one be 5 cubed plus 2 times 5 squared. 125 plus 50 is 175 minus 25. 153. So my average rate of change here would be 153 minus 3 over 5 minus 1, which would be 150 over 4, which would be 3, 5. Oh, okay. Yeah. Sorry. It's point something. 4 goes into 153. That'd be 12 with 30. No, that's 7. I got 37.5. Is my 153 wrong? Y'all supposed to be checking behind me. I'm trying to do it on the fly. 3. There's 1. Where are y'all on this now? Simple math. See? 38. What else? 10? X squared over x plus 2 on the interval -1 to 10. F of -1. 1 over 1, which is 1. F of 10 would be 100 over 12. 50 over 6. 25 over 3. A-Rock. Two-thirds. Like this. You would love calculus. Well, functions you have to know from memory, up, down, left, right, every which way. And these are the 12. And of these 12, there are only, I think, 2, maybe 3 really new ones in here that we'll spend some time talking about, and you'll fill out the rest of them. Guessing, or are you looking at the paper? Using this. All right. I am not going to go through linear, absolute value, quadratic, or cubic because we covered that in depth in Algebra 2, but I do want you to fill out the analysis for those. On the back, square root, cube root, we did. Reciprocal, we did not. So I'm going to take some, did we do reciprocal? 1 over x? No. Okay, I want to take some time. Let's start then at reciprocal. The parent function for reciprocal. In other words, what's the equation? 1 over x.
Whoa. I thought you were waiting.
You've been going a long time. I did? Oh, that's because we did it in my class. And I had them write down someone that inspires them. I think they were just sucking up. Okay, well, thank you. All right, so your homework is this whole, both of these sheets front and back, but we're going to run through the ones you don't know yet. Okay? So we're starting with reciprocal, which is on the back of the first sheet down towards the bottom. All right. So reciprocal parent function is 1 over x. There are asymptotes, both vertical and horizontal asymptotes on the x-axis and the y-axis, as is drawn here. What is the domain of this function? Negative infinity to 0, that's exactly right. U, that's exactly right. Okay, range is exactly the same thing. Yep, for this reciprocal, until we start, now of course we're going to start transforming them soon enough, but for the parent, yes, that's it. X-intercepts. And I'm just going to kind of read some of this to you, so it'll be up to you to write it down. X-intercept, what'd you say? None. It never, if there's an asymptote on the x-axis, it's never crossing the x-axis, so there's none. How about a y-intercept? None. That's right. All right, when I say extrema, what do I mean? It's the minimums and maximums, that's right. What are the extrema on this graph? There aren't any, right? This function is actually always decreasing. In order to have an extrema, you have to stop decreasing and start increasing, or vice versa. So no extrema here. Increasing intervals. As you move, none. That's exactly right. As you move left to right, there's never a time when I go up. But decreasing intervals, there you go. That's exactly right. You got to do, bless you. You got to do the domain for the increasing intervals, because if there doesn't have a graph, it can't, not increasing, decreasing, sorry. Okay, where'd I lose you? Okay, so decreasing. As you move left to right, the graph is always going down. There's never a time whenever it starts going up. So as long as there's a graph, it's decreasing. So what I would say is it's decreasing on the same thing, the same interval as its domain. So I would just rewrite the domain for the decreasing intervals. So negative infinity to 0, and 0 to infinity. How about the end behavior, because it's a little bit different here with these asymptotes. As x approaches infinity, f of x, you're exactly right, Anna, f of x approaches 0. The other side, as x approaches negative infinity, 0 again, that's right. Because as I move to the positive side or the negative side, that graph is getting closer to 0. It's not going up or down, it's getting closer to 0. How about discontinuities? Does it have any? Yes, what kind? Not jump, close. Infinite. It's an infinite discontinuity because of the asymptotes. If it has asymptotes, if it has more than one piece with asymptotes in between, that's what we call an infinite discontinuity. It's at 0. You don't look at that one because we're talking about functions and functionality, so you would only look at the vertical like that. We always look at where the discontinuity occurs in terms of x. Is it even or odd? Odd. That's exactly right. You can look at that graphically or algebraically. Questions about the reciprocal function? All right. It's odd. It has rotational. Yeah. I'm going to let you handle exponential because we did that. Let's look at logarithmic, because I think we did the algebraic part of logs, but we didn't get to the graphs. Did we get to the graphs? It's okay. We can do it anyway. The parent log at the top. Yeah. This is going to be a base of 10 because that's our common log, right? That's the parent, yeah. And I've got this graph. We don't transform the parent quite as much because We changed the base and whatnot, but anyway. What's the domain? Zero to infinity. Does it include zero or no? No. How about the range? Negative, y'all are not filling this. Negative infinity to infinity. How about the x-intercept? 1. It's 1. It's a log. Why is it 1? X-intercepts happen where y is 0. So if I do the log of x, if this is a base of 10, whatever the base is, it doesn't really matter. 10, remember changing the form? 10 to the 0 power equals x. So 1 is x. So the x-intercept is at 1. Remember, log base b of a equals x means that b to the x equals a. I know y'all remember that. Y'all are looking at me like I'm crazy. Remember we did it, and I said, look, it looks like an e to put it in exponential form. Are you bullying people, Sullivan? All right. For what? Do 2 to the x. No, let's see, 2 to the x. All right. What about y-intercept? There is none. We're on the log one. None. Because there's an asymptote there. Does everybody see that? How about extrema? None. Increasing intervals. Zero to infinity. That's exactly right. Guys, y'all gonna have to turn this in tomorrow, so make sure you're writing it down. I'm telling you what to write. Increasing intervals, 0 to infinity. That's exactly right. How about decreasing? None. None. How's it what? All right, so this is where it gets sticky. I can do the right side easy, right? As x approaches infinity, what does f of x approach? Infinity. That's exactly right. But x never goes to negative infinity. Do you see that? It goes to 0. So I'm going to say as x gets closer to 0, what does the graph do? Negative infinity. That's exactly right. So in behavior looks a little bit different on the logarithmic one because of the asymptotes. Yes, that's this part of it. Yeah. Well, we just right. Say again? Yeah, but we're gonna do the hard ones together. It's really not. It's quick. How about discontinuities? None. Can you draw it without lifting your pencil? Yes, right? Even though there's an asymptote, it doesn't break the graph up, okay? Is it even odd? Neither. It's neither. This one's neither. All right, let's do greatest integer. I saved the best 3 for last. Y'all don't know, we didn't cover that in Algebra 2? One class got to it, I remember. There's the parent function. Greatest integer is the very next one. Some people call it a staircase function, a step function. Okay. All right, so here's what it does. A step function takes every value. That's the parent function. Yeah. If I put in a decimal, it rounds it down to the nearest integer. Okay, so I'm on the greatest integer function. That's how you write it. That's how you write greatest integer. So they mean whatever you put in there, round it down to the nearest integer. So if I put 1.2 in here, it's just 1. If I put 3.95 down, 3. It always rounds down. Okay. So what this ends up looking like. Now, if you plug the integer itself in, you just get that value back out. Okay. So when x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 2, and so on. But what's happening in between here? Well, it's 0 up until you hit 1, and that's when it jumps up to the next one. And then here it stays 1, because see, if I put in 1.2, I'm right here, right? 1.2 is still 1. It rounds down. And then it doesn't jump until I hit 2, and once I hit 2, it jumps up to the next one. And that's why it looks the way it does. There are no decimals or fractions for y values. Okay? For x, for the domain, yes. So for my domain here, I could put anything I want in x left to right, and it does not matter. Do you agree? But the range, no, it does. But it doesn't connect. The pieces don't connect. No, the pieces don't connect. All right, shh. The range here, the range is only integers, right? So what I'm going to do is I'm just going to say all integers. I think that'll be easier. I'm not going to try to teach you a new. Yeah, you can say y is a member of integers. I know. I knew it'd be a gajillion questions. So I agree. Shorthand, math shorthand. Increasing, extrema. So what do you say? None. None. No extrema, because it keeps going forever and ever and ever in both directions. Huh? X and Y intercepts. X intercepts. And everything in between. It's crossing the x-axis at all these places. Okay? Y is 0. That's your y-intercept. Say again? Because what happens at 1? It jumps up and it's right here. So there's a hole here at 1. On the parent, yes. But of course, we're going to start manipulating these soon. Of course. Don't worry, we won't forget. How about increasing intervals? I'm going to say none, because each of these pieces of the graph It just jumps. It doesn't increase, it just jumps. And it's constant. Jump constant, jump constant, jump constant. So I'm going to say none there. Decreasing, definitely none, right? Don't worry about end behavior on this one, scratch through that. I'm not even going there today. Huh? Huh? Can I do it, the end behavior? You would have to define it as being integers only. You'd have to say as x approaches infinity, y approaches, but then you'd have to, I'm not real sure how you would define. Yeah, you'd have to define an infinite integer. I will. I'll get back to you. I don't know how to do it right now. I'd have to think about it. Okay. None. None. What are we on? Discontinuities. Jump. That's why I kept saying it jumps to the next one. Even, odd, or neither. Odd. It's odd. If you flip it upside down, it looks exactly the same. All right, are y'all ready for the hard ones? This is brand new, huh? Jump. You can just put jump because it happens at every integer. Yeah. Huh? If you turn it upside down, it looks exactly the same. So see, my graph is in the top right, right? If I turn it upside down, my graph is still top right. Yeah. I could go odd or neither on that one. I could see your reasoning for either one. All right, ready? No, we're going to do sine and cosine. The parent function for what? Log base 10 of x. As x approaches infinity. I can agree with that. Right. I don't know that I've ever seen the end behavior defined in anything I've done in math, like the greatest integer function, or used it for anything. That's why I said it's really not, I don't know. This is a copy and paste kind of thing of the. All right, let's do sine and cosine. Ready? We will get into, by the time we finish pre-cal, you will know sine and cosine and tangent and all the other trig functions so well. But for right now, I'm just going to give you some values and tell you what they do, and then you're going to start repeating those values on here. But I do want you to understand a couple of them. So we measure, right now, you measure angles in what? Degrees, okay? In trig, we measure our angles in what we call radians. It's a different way to measure degrees, okay? Whereas a circle has how many degrees? 360. It has 2 pi radians, okay? So an entire circle, I'm just kind of telling you where this stuff's coming from. We'll delve way deeper into this in a little bit. But the circle all the way around, 360 degrees or 2 pi, okay? We're going to use those pi values to find our sine and our cosine. So I think I'll do you a little chart so you can see where this stuff is coming from. That's the parent function, sine x. We don't put the e on it whenever we abbreviate. We just put sine x. All right, so here's what I'm going to do. I'm putting, Charlie Ray, you better know how to do this. Always. Each tick, good Lord. Is that what you said? What'd you say? Did you say good Lord? All right, every tick mark on the graph is a half a pi, okay? So I'm going to start at 0. A half of pi or pi over 2, same thing, right? So then I'm going to go to pi. What would the next one be?
What the heck?
No.
What in the heck? Okay.
All right, listen.
A trig graph. A trig graph looks different than a regular graph because I use different units. Okay. Every tick mark. You're good at math? No, bro. I don't know what spell it is to learn. Okay, well, literally this class. You just wrote down random stuff. There's no way that that's actually something. Why is pi over 2? That's my question.
Okay, I can explain it to y'all and then give you the quiz, or I cannot explain it and still give you the quiz because I still have to teach you this. Okay. What's half of a pi? Pi over 2, right? Okay. If I add another half a pi to it, how many pi's do I have? 1 pi. If I add another half of a pi to 1 pi, 3 over 2 pi. No, you can't ever do decimals with these.
Whoa, what?
Okay, ignore the pi. 1/2. If every tick mark was 1/2, right? What would the next tick mark be? 1. What would the next one be? 3 over 2. What would the next one be? 2. What would the next one be? The only difference is I'm putting pi's with these. Charlie, y'all, if you don't want to listen, pay attention, that's fine. But for those that do, be respectful. This is frustrating for me because y'all don't understand, but you don't understand because you're not paying attention. No, go ahead. No, this is yes. Okay. So I know that's what I'm trying to tell you. They always go by that unit. They always go by that. Okay. All right. The sign of 0 is 0. The sign of pi over 2 is 1. The sign of pi, look at your graph. 0. Thank you, Slade. Look at your graph. Look at your graph. Look at the graph on your paper. On your paper.
I can't read that.
All right, everybody listen. Every tick mark on your graph is a half of a pi. I have literally given you, this is the first tick mark, that's the second tick mark, that's the third, that's the fourth, and so on. -1, what's the next one? 0.
1.
The other one goes off the graph, but what do you think it would be? 1. What do you think the next one would be?
0.
So there is,
Yes, right. What's the point of that? What sign?
I'm telling you, I have never, it has never been like this.
What's this?
It's a sign. Sine is a trig function. You should have learned about sine in geometry. I'm sitting there behind my Y'all got five. Right triangle trigonometry. No.
Well, God, what do you say?
All right.
You feel like that?
All right. If they would just let me get through it, what I need you to know right now is not that deep. Yeah. It's the opposite over hypotenuse. Cosine is adjacent over hypotenuse. It's just an acronym to help you remember a right triangle trait. All right. So, I've got these points and I can see the pattern in them, yes? At this point, I'm not asking you to understand why sine of 0 is 0 or why sine of pi over 2 is 1. I'm telling you that's what they are, okay? Your calculator will do this for you. If you take out your calculator, make sure you are in radians. Yeah. Like hit mode, hit the button mode. Make sure radians is highlighted. Okay. Now come out, radians. And then, yeah. Yes, it's a function. It's a function. All right, so now if you hit sine 0, what do you get? Hit mode and make sure radians is highlighted. Say degrees or radians. Make sure radians is highlighted. Come out of that and then do sine 0. Yeah. And hit enter. It's 0. Do sine pi divided by 2. Second sum. It worked. You would have to switch it back, but no, it's good to, from this point forward in your math career, you will probably always need to be in radians. Degrees are very elementary. That's all, is whenever you're doing trig functions for right now. That's probably the only difference. Yes. Yeah. It's not. All right. Bro, I'm trying. I can't get through it. Cosine is the same, but cosine flips a little bit differently. That's the parent function for cosine. It's exactly the same. It's just been shifted a bit. I haven't because I'm worried I'm not going to get through it because everybody has not cooperated today. So you might be on your own for some of that. I'll get through what I can. I'm going to define cosine and then I'll come back to domain and range and all that. Yeah. Yes. Inclusive. So these are the same points, but they're shifted, right? So at pi on my graph here, 1, and it still starts rotating those same points. What's over 2? If you could just take the sign and just slide it over a half a pi, you have cosine. Right? You see what I'm saying? Actually, if you slid it to the left, not the right. What you going up for? Left. Left half a pi. Left half a pi. All right, domain and range is the same on both of these. Domain's negative infinity to infinity. Range is -1 to 1, inclusive, brackets. That's exactly right. Looks like this. X-intercept for sine. Okay, so this is important, and we're really going to delve deep into this pretty soon. Every whole integer of pi, so here's how I'm going to say that. X equals k times pi. Whatever variable you want to put in there, but I'm going to say k times pi, but I'm going to come off to the side and say k has to be an integer. That's the x-intercept. Because it happens every whole pi, right? Cosine's a little bit different. So you're right. Well, not every half pi. So this is pi over 2. This is pi. This is 3 pi over 2. This is 2 pi. So there are a myriad of ways that you could define this, okay? But we're going to try the easiest way. We're going to say the x-intercepts happen at, what I would do here is I would say pi over 2 plus k pi and define k being an integer. So what that says is that says start at a half a pi and then add a certain number of whole pi's to it or subtract, okay? And you'll always be at an x-intercept if you do that. That's your x-intercepts. Now we're adding a half pi to it. That's exactly right. Y-intercept for this one? Just one. Just one. Yes, for the y-intercept. All right. Increasing. Oh, did I miss extrema? Extrema. So what we say with this is we say it has an absolute max of 1 and an absolute minimum. And we don't say where that's happening because the function value itself is there and it's continuous and it goes on forever and ever and ever. But we say that it does have an absolute max of 1 and an absolute minimum of negative. So there you go for extrema for both of them. Yeah. Right, both of them. Both of them absolute max at 1, absolute min at negative 1. No. Here's your cosine x-intercepts. Here are your sine x-intercepts. Because look at where they're happening on the graph. Look at the graph and how they're occurring. This is pi over 2, and this is pi. You see what I'm saying? Remember, everything slid. So because everything slid over, I accounted for that way. Yes. Every whole pi on sine is an x-intercept. This is 0. That's really right. All right. Can you do what? Increasing intervals. Here's where I told y'all these were hard. These last two are the hardest. They're brand new. You've never seen anything like this before. I don't even make it that hard. If I'm here's how I do increasing, decreasing. Huh? What do you think? Look at sine. What do you think about sine? Odd. Sine is odd. What about cosine? Even. If you hold it upside down, does it look exactly the same? In other words, look, my first high point happens right to the right of the axis. If I turn it upside down, my first high point is still to the right of the axis. So it looks exactly the same upside down as it does this way. So it's odd. Even means you could fold it in half and both halves are exactly the same. So there's a mirror in the middle. Cosine's even, sine is odd. Oh my gosh, what class are you sitting in? This is what happens when you watch a movie and you miss your little pieces of things that come in class.
I watched your whole lesson over again.
You didn't watch it over again. You never watched it the first time, buddy.
I watched your whole lesson for the first time.
Yes, let me tell you increasing and decreasing, because I'm not going to make it with the variables any harder. Let me start with decreasing so you see. And I'm going to start with this interval right here. Do we agree that on that interval, it's decreasing? Between those two lines I drew, okay? I'm going to define that between pi over 2 to 3 pi over 2, yes? I'm going to join that. When is the next time that it will start decreasing? I'm going to have to draw some more of this graph out to be able to see this. This is 5 pi over 2. This is 3 pi. So it goes up and back down. It's doing this, right? So from here to here, it's decreasing again, right? I'm going to put a u between, and I'm going to go 5 pi over 2 up to 7 pi over 2. And what I'm going to do, as long as I have two intervals, I'm just going to put u dot, dot, dot. I'm going to put u dot, dot, dot to let it know that I keep up with that same pattern in both. It's not technically the right way, but I am not getting into all that. We're going to just leave it at that for right now until we don't get into it. Same for decreasing. All right, so tonight